Hello and welcome back to the lab for part 2 of this DMM. There was a lot of interest in this little meter, far more than I thought, and also some people commented and pointed out a few things that need to be addressed in a part 2 video. Also, we weren't done yet because it's not aligned and calibrated, so we do need to take care of that. Now, part of the reason for that is I was waiting on some parts which have come in. These are 100 microfarad, 10 volt radial bipolar capacitors. The part number is UVP1A101 MED, sourced from DigiKey. And they are, I believe these are Nishikans, is what I bought. Yep, they are Nishikans. Okay, cool. So there were some comments brought up in the previous video, and people asked me to go in depth on some more topics. So we're going to do that in part 2 as we finish up this meter. So a couple of the quick notes that happened is the display is not a dot matrix display. It really operates like a 7-segment display, but instead of being a true 7-segment display, this display is a 7-segment dot display. So a little bit of terminology kerfuffle there. One other thing is, it is true, this top half, so the multimeter part of this unit is the bottom half. This top half is just a meter. There is nothing multi about it. All this is a meter that measures from, I think it's 0 to 10 volts, if I remember correctly. And that's all it is. So no DMM in the top display. It's just a meter. What was being shown on the oscilloscope in the prior video was not the noise floor of interest. The noise floor was just the noise floor. We're actually looking at clocking signals, and I'm going to pull up a schematic here in a second, and we'll talk about it. But I guess the camera angle and things were bad when I was recording it, and the pulse width is very, very short. So we were checking for activity because in the previous video, the display was just completely dead. If you're running across this video first and you haven't seen the previous video, take a look at the previous video, and it'll give some context for this video. So the display was completely dead. Now, we did confirm we had data, and I'll get a schematic right now, actually. So as we take a look at some of the schematics, no, I have not mastered the art of elevator music yet, so you will have to bear with me. At U9, we had data. So from U9, it goes to U3 and then to U2. And I also had data. So U9 comes in to drive U3, and then U3 drives U2, which is the character generator. I had activity that looked like the display should have been moving. Now the display itself was stuck at all zeros. So that's what led me to U2. So I hooked up 2 of these address lines to the scope, just looked, and I did see serial data moving around. Maybe not exactly serial data, but what would be data lines. So what that told me is there's not much between U3 and the display itself for me to have what should be data. I maybe have garbage up here, but I shouldn't have a frozen non-zero display. Or a frozen zero display, because that's all it was. So there's really only 2 things that can cause that. One would be no clock, because if these ICs aren't clocking correctly, they're not going to shift when they're told. Or a bad U2. Now, U2 is a custom IC from HP and would be incredibly hard to source a new one and swap out. So I was really hoping it wasn't U2. So I went the other way, which was fixable, and I started checking the clocking and timing, which starts out at U20. We do some stuff in U16. So this particular unit uses 3 different clocks and it's all divided off of a main clock. So the main clock starts up here in the timing generator, and then through these flip-flops, it divides down, and so it gets slower and slower and slower for different functions in the display. All I was looking for on the outputs of these chips was clocking. So the thought process there was, if I have data and I have clock, there's really only two things left. So if I have data on these pins and I have clock where I should have it, U2's got to be bad, or the display itself has to be bad and it's not switching. U2 did not come out well. That was not the fault of the unit or anything like that. I'm pretty sure that was a technician error in getting that out, and especially with it being a ceramic package, was not easy to desolder, and came out poorly, which is how we had to swap displays and finish the repair to get a functioning meter. When it comes to buffing plastics and buffing the displays, I've talked about this a little bit in a couple of extra videos, but if you just found this video to start with, I can understand the confusion. And some of these techniques, if they're important enough and there's enough interest, I'll break them out into their own separate videos and we can talk about them in depth so they're easier to find later. Polishing plastic is somewhat easy, but also somewhat difficult at the same time. Plastic can be burned pretty easily. Actually, some of it, depending on the plastic, acrylic, can be flame polished. Some of it can be polished with acetone, chemical polished. If you search YouTube chemical polishing of headlights, you'll see a whole bunch of plastic that clears up with acetone. So there are many, many, many ways to polish plastic. Typically, the way I do it is the mechanical method. So I wet sand, taking it up the grits. This is emery paper, so it's designed to be used wet and dry. We have 800, 1,000, 1,500, and 2,000 grit emery paper. And you just take it up the grits. If you do it wet, it keeps the dust down, keeps everything from clogging up. Works really, really well. For wetting, as soon as I find my squeeze bottle, well, I'm not 100% sure where it went, and I swear the lab sometimes eats the most random things. I have a squeeze bottle with a blue top, and it's just straight distilled water. So distilled water on the emery paper, buff up the plastic. That will not clear the plastic up. 2,000 grit is not fine enough to clear up the plastic. It'll be smoky and white. Should be noted, some plastic. Well, I can't find that either at the moment, so the lab is not being nice today. But if you use the wrong chemical on the wrong plastic, it can smoke out and essentially smoke up the plastic and make it look bad. Some of the more harsher chemicals, acetone, lacquer thinner, things like that, are much harder on the plastic, but we go with distilled water. After the 2,000 grit sandpaper, we move on to a buff wheel. I'm really going to fix my buffing setup. I do not have a good buffing setup right now. I want much better buff wheels, things like that, but I'm rapidly running out of space in the lab, and I need to work on what we're going to call the dirty side of the lab, essentially some of the fabrication work, things like that. And we've got the clean side of the lab, the bench, everything like that. It's in great shape. The dirty side of the lab is where I need to put some work in, and definitely have a lot that still needs to be done. But this is one of my buff wheels. I have several sizes. This just gets some buffing compound. It's nothing special. It's a soft cloth wheel. But I chuck this in a drill press, and I have a good drill press that gives me some high speed, goes up to about 2,000 RPM, and I can buff out a lot of things with it. Don't run it at 2,000 RPM. That generates a lot of heat at the buffing interface, and it's easy to burn and melt the plastic and cause yourself bigger problems. So you have to be really careful when you're doing high-speed buffing of plastic. It's very easy to melt the plastic. The other thing is you got to be really careful with the drill press. Drill presses, the bearings in a drill press are good for forces that go straight up and down. They are not specifically made for side loading of forces. So if I have a buff wheel in there and I'm side loading, I have to be really careful how hard I'm pushing because I don't want to damage the drill press. So most drill press bearings, unless they're designed to be mills, that's one of the differences between a drill press and a mill, is mills are designed to cut sideways, front and back, so that they have bearings set up for side loading. Drill presses do not. They're designed to punch a hole straight down and very accurately punch a hole straight down. So the side loading can be a problem if you put too much force on the side. Okay, if we take a look at the power supply, we have a bunch of ground symbols along this power supply. However, when I measured the ground on this unit and measured it versus earth ground and found out it was a non-zero ground. So even though this is circuit ground, this is not chassis ground, and it is also not earth ground. That causes my scope some problems. So we'll take a look at the front of a scope. So on the front of a scope, pretty much every scope, unless it's an isolated ground scope, the barrel of this connector is registered to earth ground through the chassis, through the electric panel, out to earth. So in a measurement context, the scope is single-ended. So we're taking whatever's on this center pin, and we're measuring it versus what's on ground, which is the outer shield. Because it's earth ground, and this is circuit ground and the power supply in this particular unit is floating, and when I measured it, there was a non-zero voltage and a non-zero current there. Was minimal, but it was also non-zero. I didn't want to skew anything up or short anything out by connecting the earth ground of the scope to any point in the circuit to pick up a ground. When I measured, this caused a ton of problems on the display. It was horrifically noisy, couldn't trigger. It was just awful. All kinds of 60 cycle buzz, just noise beyond. So what that had to mean is the noise was present in the power supply. So the signals that I was seeing on the scope were real, but they weren't what I wanted to measure. I was measuring common mode signals of a floating supply with a piece of equipment that was referenced to Earth. So it was throwing the measurements all out of whack, and I needed to take care of something. Enter the mixed sig high voltage differential probe. So essentially what a differential probe does is it takes the single-ended input in your oscilloscope and makes it measure like a DMM between 2 points. So it raises it from earth ground, lets it float, and allows you to make differential measurements as opposed to single-ended measurements on a power supply that may not be referenced to earth, which is what we found in this 34702. Now essentially, I had to use the Rigel for this because this is not unpowered circuitry. We had to hook up a USB cable, which it comes with, and had to run it up to the scope so we could power the active circuits in here and allow it to measure. Now, I believe I did it with the 5 megahertz limit turned on to couple out the noise, but then also the reason to use the Rigel to get the ranging right. This is a 20x and 200x probe. It's the DP10007. It will work with a tech scope, not a problem, as long as you use the external power brick to turn the circuits on, because it's designed for 1 mega ohm up here. But this 20x and 200x, the display readout's going to be wrong, the switching's going to be wrong, so you'll have to do some compensation math to get the ranging right. The Rigel, I can actually set 20 and 200x, so I can actually get the ranging right. Also remember, when looking at these are an attenuation factor, not a multiplication factor. So when you set it to 20x, it is a 20 times reduction in signal between here, well, actually here and here. 200x is a 200 times reduction in signal between measurement and scope. So it's how we can extend the range of oscilloscopes well beyond what they're supposed to. There are a couple of scopes that have this capability built in. Most of the time, you'll find they're for heavy industry, essentially panel work. And having a scope with an isolated input is actually fairly rare, and they will spec that. And you'll also notice like this barrel might even be insulated in plastic, a couple other things. So if you have a scope with an isolated input, you'll know it. If you don't, if you think you may not have an isolated input on your scope, you probably don't. It's probably ground reference. 99% of the scopes you're going to run into, unless you ordered something specifically isolated inputs, are going to be earth referenced inputs. Because these signals were common mode, using the differential measurement, it was on both terminals, so the noise canceled out, and I got good signal measuring the clocks. I could safely hook up the negative to ground, look at the outputs, referencing the ground, and keep everything there without shorting out the circuit, killing anything, or potentially doing some damage. This brings us to what we have to do tonight. So what we got to do tonight is pop this back out, if I can, without too much trouble. What we need to do is these capacitors need to get replaced. They are 100 microfarad, 6.3 volt capacitors, and they are bipolar, which is why I didn't have them in stock in the lab, so I have to get those swapped out. Measuring these from the other unit, because I still have it, they are starting to show some internal leakage, so we're getting high leakage current, which is affecting the meter a bit. Working in this section, I'm going to have to clean this off with alcohol when I'm done, especially right in here. This is an incredibly high impedance section of the circuit. We have a Teflon wire. We have standoffs, Teflon standoffs. So I'm going to minimize the amount of handling that I have to do on here. It's okay to touch the caps. They're getting replaced anyway. But we'll get these things swapped out and then let this unit do some more burn-in. Then we'll be on to an alignment and calibration. Going to try to do this since there's only 3 capacitors. We're going to try to do this on camera. So pardon in advance any of my awkward photography while I'm focused on not burning myself. Well, that just fell out. Okay, using a quick Atlas test. Let's see what it says. Okay, our ESR is starting to drift up a little high, but I'm more concerned with this number right here. This is supposed to be a 100 microfarad capacitor. This is measuring at 141. That means there is leakage current there. This particular unit, the way it measures, if a cap has excessive leakage, it'll show artificially high capacitance value. Not necessarily a, quote, bad capacitor, but given the sensitivity of this circuit, that's too much leakage. Testing a good capacitor. We have a little bit more ESR, but our leakage is lower, and we're measuring 96.3, which is fine. This cap is 20% tolerance, so it is within spec. Bipolar caps are a little weird pieces of equipment. Okay, so we have some traces I want to be concerned about. So I'm going to insulate this with, I'm going to stand it off a little bit better. Let's do that. Okay, while we wait for the solder gun to heat up, we have air gapped this cap off the board. Also, they went up in a voltage, so these were 6.3s. These hundreds are 10 volts, so we got a little bit more. Didn't get much more capacitance, but we did get some more voltage, which will be good. And we'll air gap the rest of them like that, and I'll bring you guys back when the soldering's done. All right, caps are in and cleaned up. Everything's good and ready to go back, put back together, and hop in the case. We're going to let this do some burn-in testing overnight. Not overnight, but for tonight. If everything goes well, we'll fire up the Cal gear tomorrow and give it an alignment. All right, moment of truth. We have 9 volts on the leads. Oh, helps if I turn on the power supply. I'm good with that. So we're just going to let that sit for a while, make sure everything's all right. Then we got to warm up the cow gear. Not going to warm up the cow gear tonight just for the length of time it takes to warm that gear up. It's on a minimum of an hour and a half warm-up time for the 7.5 digit meter, the AC and the DC ranges. So we're going to let it run. And then we'll talk about, once we do the alignment, we'll talk about what this is replacing. And taking a look at the service manual for the display unit, because we have two separate meters, we need to do two separate alignments. The top half being a 1-volt meter, the bottom half being a multimeter. This board is incredibly different from what's in the service documentation. There is no voltage adjust, there's no other things, so not much I can do on this top board by way of adjustments. They are on the back. But the unit needs a 2-hour warm-up before adjusting the top board. So that's what we are going to have to do, and it needs a 2-hour warm-up with the case closed. So I need to pop this back in its case. Without banging the transformer too hard. Wrong screwdriver. And we'll get the meter put back together. Have to pull the rails out. There it goes. Okay, we'll let this warm up, and then we'll do the plus and minus adjustment. The plus and minus adjustment is very simple on this particular meter. It's plus and minus, and it's set at 1 volt. So 1 volt from the standard goes in, and then we set this for precisely 1 volt on the front of the unit. Okay, looks like our 1 volt rail needs adjusted. Not rail, sorry. Our 1 volt range needs adjusted, both positive and negative. We're out on both sides. This is okay to handle because it's only a volt, but I am far more cautious when we have to crank this up. Being a meter, we are going to have to align the 1,000 volt rail and all, or rail. I don't know why I keep saying rail. 1,000 volt range, and put some spicy voltages into the front of this thing. But for now, everything's safe and handleable. Okay, I'm on the plus potentiometer on the back. Not a very touchy adjustment. This will be pretty easy to line up. Go a little further. Come back, and I kind of want to do it by feel, but I want the potentiometer centered right between 9999 and 1.001 to get the best accuracy. I'm just being picky, but that's what we're shooting for. Exact same thing on the negative side. All right, here's our negative side. Too high, bring it back down. There's our 1 volt. There's that. So we bring it back. Just when doing an alignment like this in a calibration, just pushing on the potentiometer can actually cause readings. So I'm tightening up my arm, pushing on the pot, and we have some movement. I'll take the screwdriver away. All right, so this, because it's jumping right here, it's a little borderline. I want a little bit more signal here. So what we'll do, now I'm trying to adjust it this way without putting too much lateral load on the potentiometer, because that can actually skew the reading. So I'm not really pushing on the screwdriver, it's just resting on my finger. And we'll pull the screwdriver away, and there we go. All kinds of weird and interesting things happen when you're doing an alignment and a calibration to get the most accurate results. Just waving my hands around here will cause the reading to jump around a little bit. That's normal. Okay, I mentioned earlier about how using the wrong cleaning material on plastic can destroy the plastic. I used acetone to try to clean off a sticker off of this micro screwdriver set, and I just nuked the front end of the plastic on this. So very glad I made the mistake on an ancillary piece of screwdriver equipment and not a rather nice conditioned piece of test gear. But be careful what solvents you use on plastic. Okay, the alignment process on this particular meter is relatively straightforward. Give it appropriate sources on the correct inputs and adjust all the points on the meter board. Voltage, so we have 100 volts DC, 100 volts AC, 10 volts DC, 10 volts AC, 1000 volts DC, 1 volt AC, and then we have the resistance ranges. 1000 volts DC coarse and 1000 volts DC fine. Yep. And the resistance ranges. So we are going to have to put some spicy voltages on here. If you are following along, you are doing so at your own risk. These voltages and these generators can be lethal if you come across the voltage in the wrong way. I'm going to be extremely careful. Pretty much once I get done with the 10 volt range, it gets spicy. And I have to put 1000 volts AC as opposed to 1000 volts DC on the inputs of these meters. So the generators are putting out 1000 volts AC and 1000 volts DC. So if you are following along, you are doing so at your own risk. You have been warned. I have done this for quite some time, and I am very comfortable working on high voltages and taking the necessary precautions. But one does need to be careful. Electricity doesn't often give second chances, especially high voltage, high power. So I'm trying to do this alignment, and I threw the meter together again, thinking I may have shorted something out, broke something, and was kind of tearing my hair out because I'm like, the meter worked. I go to set 10 volts, and it doesn't read anything. And I had just set 10 volts on the DMM 7510, and literally, as I move the cable, the wire breaks. So this is why sometimes the lab just reminds you what can happen. Well, when we have a meter cable that works, it works a little bit better. We'll let this warm up a little bit more before we do the alignment, because I did have it off for a little bit, so it does need some warm-up time. This is looking pretty good for the 10 volt range. Well, looks like we can leave the 10 volt range alone. Let's check the 100 volt range. Okay, when I turn on the standard, the 100 volts should be applied to the test terminals. Here we go. Looks like that needs a little bit of adjustment. 100-volt DC adjust is this potentiometer right here. That's the 1000-volt pot. Whoops. Wrong pot. That's okay. I need to adjust the 1000 volts next. There's 100. We'll preliminarily set the 1000 volts, although preliminary set it to 100 volts. And we'll check the 1000 volt range next. Now that we got 100 volts DC on there, we're going to turn this source off before we start touching the connections. Okay, here's 1000 volts. Not too bad for testing it or setting it at the bottom of its range. Kick this up to 1000. Right there. All right. Well, that's the DC ranges. Next is the AC ranges. Okay, our 1 volt AC is going to need a little bit of adjustment. And there we go, 1 volt AC. That's going to look good. 10 volt AC is going to be this capacitor right here. All right, we'll turn the 5200 on to 10 volt AC. That's going to need some tweaking. I'm going to get a low capacitance screwdriver to do that one. All right. Capacitor is really stiff. I'm going to be good with that. $100 volts AC is going to be this capacitor right here. Okay, turning on the source. A little tweaking, but not too bad. Nope, overshot. Extremely fiddly adjustment. That'll be good right there. I'm good with that. All right, I got to get the big guy out now, so we got to do the 1000 volt AC range. For those that are new to the channel, just finding it for the first time, these are the signal sources that I use for doing these alignments: DC, AC, and high voltage AC. This guy puts out a lot of heat. Actually, he puts out enough heat where ACAL on this one got cranky, and it wants me to run ACAL on the 7510. So this is a 7.5-digit DMM, which I'm using as a transfer standard for the DC source. The AC source up to 100 volts. This and this are coupled together, and I have a 1000 volt AC source down here. Now it does have its own cable, and all of the cautions on this cable need to be very much understood and followed. This is some extremely spicy voltages. We've got 1 kilohertz AC at what's going to be 1,000 volts. So I do have to take a lot of precautions to not get zapped. One of which is turning off the source before I touch the leads. Okay, so limitation of the Keithley 7510, it only goes to 700 volts. So it can't measure 1,000 volts AC. So we are going to have to adjust this at 700 volts and call that good for now, because I don't have a good way to validate 1,000 volts AC at the moment. All right, so we have a capacitor in here that we need to tweak. This is the course adjust. If I could get on it. That's not bad. I'll take that for 700 volts. Okay, we do need to come down a little bit using the transfer standard. We were at 9.77. And that's looking pretty good right there. Okay, to get the 10 meg range set, just used a fixed 10 meg ohm resistor. The 7510 told me it was 10.0738. So everything is fine with that, and this meter is good to go. Okay, so what are our plans for this tiny meter? One is, for what it can do, it's a pretty powerful meter in the form factor. So it's a nice compact form factor. And for the job that I need this meter to do, I do not need shunt resistors. So I don't need to measure current. So the DC volts is primarily where it's going to live. And everything's going to be fine. The meter it's replacing is this giant fluke right here. This is a 6.5 digit fluke and was way overkill for what I was using it for, so this meter is going to take over that function. Essentially what this was on a workbench where primarily the repair task that was done was going through UPS batteries, checking lead acid batteries, making sure they were okay, and doing some load testing and discharging and things like that. So complete overkill for that task. This will work just fine, nice small form factor, and it'll live again. So this is going back into production, not in this facility, but in a different one that is actually currently being renovated at the moment. So this is going to hang out here for a little bit, and then it's going to move on to its final resting place. Thanks for stopping by the lab and taking a look at the second installment of this 34702A multimeter. If you've got this far in the video, think about hitting the subscribe button and hanging around. There's a lot more to come, and we're just getting started. If you'd like a little bit more content, check out the Patreon page. Patrons are running ahead for YouTube. There's nothing behind the paywall, so all videos will eventually make their way to YouTube, at least at the time of this recording. And the help of the patrons helps keeps the light. Blah, blah. The help of the patrons keeps the lights on in the lab and videos coming to the channel. So, as always, their help is greatly appreciated, and they have a huge hand in making sure these videos make it up to YouTube. So with that, as always, more is always on the way, and I will see everybody in the next video.